morning, everyone. I hope you
Morning.
guys had a good spring break
Good
and
morning.
you're ready for the second part of the course. So for the first 2 or 3 weeks, basically, we're gonna finish the idea of series and what we will be calling power series. And after that, the last part of the course, the last 2 weeks and a half, it will be basically the easiest part of the course, which will be conic sections like parabola, ellipses, hyperbola, parametric curve. So it will be rather easy. The hard part of the course is now. And I want you to be very, very careful and do your homework daily and ask questions, because this is really basically the hardest part of the course, those next 2 or 3 weeks. Before I start, there is, as you guys, if you go to Brightspace, there is a free tutoring. I don't know if you guys are using it, but there is a free tutoring for the class. Please, everything is, the announcement is on Brightspace. Please go over it and make use of it. The student doing the tutoring was a previous student of mine. She's very good and very nice, so she can help you a lot. So let's get going. I don't think you have questions. So we today we're gonna start section 10.4. It's called divergence. And integral test. All right, so we have a series, sigma an. So sigma an or some sigma ak, that's the series. And an infinite series, which is, as I remind you, it means we take a bunch of terms and we start adding them. That's really the definition. And that's what the sigma series. And the series converge. So this is when you read something like that the sum of those terms plus etc. equal to S. So that's the sum. It means that the partial sums, it means as you add more and more terms, this finite sum become close to S. So equal to S, it means if I take Sn to be the sum of the first n terms, means the limit of those partial sums is equal to S. Okay, it means if you add more and more terms, those sums become close to S. And that's what really convergence is about. All right. The question is, what does, if a series converge, it means when we add those terms, we get close to something. What does the convergence of the series tell us about the term, those individual terms? So if a series does converge, what does this tell me about those terms? A1, A2, A3. So I will elaborate by an example before I give the theorem. So I'm going to give you a series. Two series, one very simple and another one, just whatever. Suppose I take the following series. Sigma 1/2. K equal 1 to infinity. Okay? What does this series mean? Sigma 1/2. Means all the term is a half, plus a half, plus a half, plus a half, plus etc. Now, does this series converge or diverge? Quickly.
Doesn't it diverge?
Because
it's just going up to infinity. It's not going to.
What is it?
The value an or S.
Yeah, there's a big difference. An or Sn, make up your mind.
Sn.
Right, because the sum, as we're adding, the sum of the terms is definitely going to go to infinity. The first sum is a half. A half plus a half is a 1. 1 plus a half, 1 half. 1/2 plus 1/2 is it 2, 4, and so on and so, because the sum as n goes to infinity, definitely. Now, if I take something not quite like it, but something similar. Oh, sorry, 2k, because the book is using k, it doesn't matter, I'm using k. All right, suppose I take this sum. So I think I took it last time, but I will review it. It's a third. So if k is 1, it's a third. If k is 2, is I have 2 times 2, it's a 4 plus 1, it's a 5. Plus, that's a 7, that's a 3 over 7. And 4 over 9. And it keeps going. We add more terms. I'm just going to show you like the hundredths term, for example. That's the hundredths term. The 101 term. Okay, equal 101 to 101 to 103. Plus, and I keep adding and adding. Okay. And now intuitively, this question is intuitive. Does the series converge or diverge? What do you think? Very intuitively. The idea is to start working on this. What do you think? Converge or diverge?
Converges.
Because
each of the values is going towards 0.5.
Each of this value, each of the its stands for what in this question? When you tell me its means what?
Each of the numbers 1.3.
Which numbers? Which numbers?
AN.
Okay, each of the AN goes to 1/2. It means this one close to 1/2. That's what you mean?
Yeah.
Okay, this one close to 1/2. So the numbers AK is according to your classmate, which are the K over K plus 1. Those terms become close to 1/2. This is absolutely correct. But does the series converge? What's the difference? Okay, questions addressed to all of you.
Converges because it's going to a specific number, which is 1/2.
What's going to 1/2? The terms.
Yeah.
But what a series converge if what happened?
The sum. We have to look at the sum.
We have to look at the sum, not the terms. We have to look at the sum of the terms. Are you with me? The series converge if when we start physically adding those terms, the sum of the terms converge, not the terms themselves. So the terms, you guys are right, it's becoming close to 1/2, but there's the individual terms. It means the sequence of the terms. We have to look at their sum. Now, do you think their sum will converge? What do you think? Okay, Emilia, you say no, you're absolutely correct, but you have to tell me intuitively no. And I'm sure I know that I'm doing this problem at a very intuitive level now. So the sum, the series, it means the sum. Okay. Why do you think it diverges? It actually diverges, absolutely diverges. Why it diverges? If you start you add the first 2 terms, a third plus 2/5. Okay, plug it into your calculator, big deal. You add the 3 terms, plug it into your calculator, I'm not gonna bother. You'll add 4 terms, plug them in your calculator, and I'm not gonna bother on purpose. At some point, so you'll add, let us say, the first 100 terms. then you start adding more terms. You're almost adding a half to it. Then you're adding another half to it. So already you're adding 1 to whatever you added before. Then you're adding another half to it. So you're adding 1.5. Then you're adding another half. You're adding 2. Then you're adding another half. And then you're adding another half. Then you're adding another half. Can the sum converge in this case? I want the answer. I want somebody to tell me anything.
I don't think so.
Because
Because if we're doing it the way like of S1 equals 1/3 and then adding on for each S, wouldn't that mean you're basically just adding a half each time? Or no, am I getting that wrong?
absolutely correct. That's the idea. That's the idea. It means basically at some point I will be adding what? A half to a half to a half to a half to a half. It's going to diverge. No way out. Okay, so the series, it doesn't mean, so the series is the sum of the term, not the terms. The terms converge to 1/2, the individual terms. But what I am doing, I am adding them. That's really the difference between the sequence of numbers, AK, versus their sum. We're adding them. So the series diverges because, so diverges, because as you guys put it, because eventually we're adding a half to a half to a half. We're adding, and I said eventually we're adding a half to a half to a half, etc., which is going to blow up. Okay, so this series definitely is going to diverge. All right. But I say instead of okay, this idea, simple idea, not very simple, is gonna lead to the following. If a series converges to the following theorem that we're gonna work on, then I'll come back. So the first important fact. If a series, if a sum, if an infinite sum sigma AK means A1 plus A2 plus A3, etc., converges. So if an infinite sum, A1 plus A2 converges, then, so if I know that the series converge, then the limit as k tends to infinity of the general term, what can we say about it? I stop right now. Suppose a sum does converge. What do you think those terms should be when k is large? So let me take you back to this and see how we can build up. So let's see what's happening. When I look at those terms, if those terms become close to a half, the series is diverging because eventually we're adding a half to a half to a half. So the question that if the series converge, what should happen to those terms?
Should I be 0?
Should I be 0? Absolutely. The terms have to become very, very small. This means the limit of the AK should be equal to 0. So if a series converge, then those terms have to be equal to 0. 1k, not equal to 0, the limit has to be equal to 0. For the reason that if the limit is not 0, so let us say the limit is 1/2, that's what's happening. It means I will be eventually adding a half to a half to a half, causing the series to diverge. So if there is any hope, the sum will converge those terms, those AK have to go to 0. The AK have to go to 0. If the sum has to converge, those terms has to go to 0. But if they don't become close to 0, if those become close, let us say to 1, then I will be adding 1 to 1 to 1. The series will diverge. If they become close to 1/4, I will be adding 1/4 to 1/4. The series will diverge. So if they converge, those terms has to become very small. Otherwise, I will be adding big terms to each other, and the series will diverge. So the first important fact that if it converges, somebody told me it converges, then the term has to go to 0. However, that's the idea that for the student become hard. However, if the terms equal to 0, the series may converge or diverge. Very important remark. Okay. It means that if you know that the series converge, immediately you can say that the terms have to become very, very small. However, if the term become very small, the series may or may not converge. So we cannot deduce anything. So let us see example. Okay. Let me consider the following series. Sigma 1/2 to the power k. K equal, let us say 1 to infinity. I'm going to take 2 examples. So this is a half plus 1/2 square plus 1/2 to the power 3, and so on and so forth. Okay, we've seen this series before. Here in this case, the general term, it means what we call AK is called the general term, is 1/2 to the k. It means we're adding terms of this form. Now, when k goes to infinity, in this case, the terms become definitely small. Okay, it means those terms are becoming small in this case. And so on and so forth. Now, in this first example, does the series converge or diverge? You should know everything about the series.
This one converges
Because
the terms are approaching 0.
no. If the term approaches 0, it may converge or diverge, and my second example will clarify that. And that's really the hard part of this whole concept.
Okay, how is that wrong?
Because the term, I will tell you, I will give you another example immediately, but I want to finish that. If the term becomes close to 0, the series may diverge. And that's why it becomes hard, because the terms, even though they are small, but they still add up to a large number. That's what's happening. And that's the difficulty of the course. And who can give me a better reason, a solid reason?
Wait, so the answer is that it converges or diverges? Because I was thinking that it diverges.
This one converges because. What type of series is that? You've seen this. You've seen it very well.
Because the geometric series R is less than 1.
Exactly. This one converges because that's a geometric series with R strictly less than 1. That's what causes it to converge. So let's write this down. So the series converge because it is a geometric series we're multiplying by a half. We're multiplying by a half. Multiplying by a half. Geometric series with the ratio R equal 1/2. So that it converges because a geometric series with ratio equal 1/2. And not only converge in this particular example, and the sum of those terms, the sum of the terms is the first term times 1 over 1 minus a half, which is equal, it means the sum of those terms is equal to 1. So in this case, sigma which is a half plus 1 over 2 square plus is equal to 1. So let us here note very carefully, note the sum is 1, is when we add them, we get 1. Do not confuse the sum with the term. And the terms themselves go to 0. Go to 0. Okay, so that's the first example. That's a series, that the only series we understand, that's a series. The terms goes to 0 and it converges. Now, example 2. It's going to be numerical because I don't have the tool yet to show it algebraically. Example number 2 is the following. Let me take the following series. Sigma, let's consider the following series. Okay. Sigma 1 over the square root of k. K equal 1 to infinity. Okay. And this is a 1 plus 1 over square root of 2, 1 over square root of 3, 1 over square root of 4, plus so on, plus so forth. Okay. Now, what's the AK here? It's 1 over the square root of k. Okay. Now, the term here definitely go to 0. So when k goes to infinity, square root of k goes to infinity, this is equal to 0. However, that's the important part. The series diverges. Okay, this series diverges. Now, in the second part of today, if we reach that, we will show you why it diverges mathematically. I mean, what caused, which test will tell us diversion. But for now, what I'm going to show you is the sum. It means if we start adding those terms, what's really happening to the sum? So to give us an idea why it's really diversion. Okay, so this is a series, that's the important one, where the terms become small, but if we start adding them, the sum is going to blow up. Even though the terms are small, but they are not small enough if you want, so that adding them will still make them go to infinity. So what the only thing I'm going to show you is their sum, just to convince you somehow that it's blowing up. So if I pick up my calculator or I use there are a lot of websites that do compute the sum. If I start computing the sum, so let me give you some values of the partial sums. So I'm going to take some values of partial sums, just to give you an idea why. So some values of partial sums are the following. So suppose I take the sums here, and I add the first 10 terms. It means I add 1 plus 1 over root 2. I just add them, physically add them, up to square root of 10. If I add those, I get 5.02, which doesn't tell me anything. Suppose I am ambitious, I don't have a lot of time, I add the first 1,000 terms. This is not a proof, that's just tell you that 1 over the square root of 1,000. I keep adding and adding, and then I'm going to get something like 61.6. Okay, so the sum is getting bigger. If I add the first 10,000 terms, and there are a lot, I mean, that's really wasn't hard to do, means I start adding. I really add. Even though I'm adding small terms, because 1 over square root of 1,000 is very small, still there is a certain contribution. So I'm adding those, it's giving me 198.54. Okay. I keep trying to add, but I realize the more I add, I'm not getting close to any boundary. Nothing is close. Those sums are actually kind of really blowing up. Even if I keep adding, I took 1 million, I realize that I'm still going higher and higher in value. The sum aren't really getting close to anything. This sum is actually going to diverge. So even though the terms become small, but intuitively, it's not small enough for the sum to add up. So far, the only thing we know that if I know it converge, the terms equal to 0. But if the terms go to 0, but going to 0 tells me nothing about the series. However, I have the following simple test. However, I have the following. We're going to call it the divergence test. So the first test we're going to learn. Divergence test tell me the following. Okay, the first test we're going to see today. Divergence test the following. If, suppose we have a series. Sigma ak. K equal 1 to infinity. Sorry. The divergence test tells me that if the term of the series, the individual term, is not go to 0, it means if the terms don't get small enough, then the series, I want to finish my sentence.
Diverges.
It's crucial. So the divergence test tells me, if you have a series, look at the terms. If the terms don't go to 0, then the series diverges. If the terms go to 0, the series may diverge or converge. So it's only give me ideas. In one case, if the terms don't go to 0, diverge. If the terms go to 0, both we can have divergence or we can have convergence. And that's the important idea here. So the divergence test is an easy test. You have a series, you look at the term, you glance at them, and you look at the AK. You ask yourself, do they go to 0 or not? They don't, you're done. They go, we're in trouble, and we have to see what will happen eventually. So before we move on to the other second test, let us ask you the following example. So questions. I'm going to give you 3 series. And the question said, use the divergence test to decide if the series converge or not. If the divergence test is inconclusive, state so. So use divergence test to decide if series converge or diverge. If the test is inconclusive, and we'll make clear what I mean by that, state so. State so. So I'm going to take 3 series, just top of my head, and decide what will happen to them. So the first example. Suppose I take the following series, sigma k squared over k squared plus 1. K equal 1 to infinity. Okay. Now, question to you. Do you think the series converge or diverge? I want you to use a divergence test. It means I want you to look at the AK. So what is the AK in this problem? It means what type of term are we adding? Here, the series, what's the AK here? It means adding those type of terms. So we're adding, if k is 1, it's 1 over 2 plus 4 over 5 plus so on and so forth. So this is my AK. Okay, we're going to look at the limit as k goes to infinity of the AK. It means those terms when k become large. This is equal to the limit as k goes to infinity of k squared over k squared plus 1. Now what's this limit? Is this equal to 0 or not? Can anybody tell me this limit by looking at it?
1.
No,
I think
yeah. You can divide by k squared, both, or you can look at it. This is equal to 1. So does the series converge or diverge quickly?
Converge.
Because
It's approaching 1.
what's approaching 1?
The values of AK, they're slowly approaching 1, but never actually getting there.
Yeah, but what are we interested in? When I ask if the series converge, what are we interested in? The sum of the AKs, not the AKs themselves, their sum. So the AK converge to 1. But the question is, what I'm interested in is what? Is the sum of the AK. It means I am adding those terms. Will adding those terms get me to a finite number?
no,
No, because eventually what I will be
Because
adding? Go ahead.
you're adding 1 each time.
Exactly. Eventually I will be adding 1. So is this series going to converge or diverge?
Diverge.
Diverge. Can we apply the divergence test? Now let me go back to it. What does it tell me? If the terms, the limit is not 0, the series will automatically diverge. Because if the limit is not small, we'll be adding not a small number. So if the limit is 1, we will be adding eventually 1 to each other. If the limit is 1/2, we're eventually adding 1/2 to 1/2 to 1/2. So we're not, so the term become close to 1, but the series definitely diverge. So the limit is different from 0. So the limit of AK, as k goes to infinity, is different from 0. So by the divergence test, the series diverges. The AK become close to 1, but this means that when we're adding 1 eventually. That's what you have to keep in mind. The AK, the stats, the individual terms become close to 1/2. It means adding them is going to blow up. So this series, we can use the divergence test and the series diverges. Okay, example number 2. Okay, suppose I give you the following series. Sigma e to the k, for example, over k. K equal 1 to infinity. All right, so this means e over 1 plus e squared over 2 plus e cubed over 3 plus e4 over 4 plus etc. etc. So AK, it means the general term here is e to the k over k. And now the question is, does this series converge or diverge using the divergence test? That's really what I'm interested in. So because that's the only thing we know. So the limit of the at k goes to infinity of the AK. So the question is, what happened to those? Okay, what's this limit here? Back to you. The first was the limit. Second, does the series converge or diverge? Quickly, guys, before I start picking student, because I want all of you to be part of it. What's the
Isn't
limit?
infinity?
Because
They're both going to infinity at a large rate, but e to the power k is going at a much larger rate.
Right.
So
okay,
still
and
infinity.
if you want to do it mathematically correct, what do we do? Infinity over infinity. We can use L'Hopital's rule. Do it correctly. So it's going to give me the limit e to the k over 1, derivative to k, derivative of k is 1, which is equal to infinity. So what can we say about the series immediately? Converge or diverge? Absolutely. All of you, converge or diverge?
Diverge.
Diverge.
Diverge. The terms are becoming very big. We're adding big terms, so the series diverges. Okay, now the last question is, the last problem is sigma, okay, of, let us say, k over k squared plus 1. So this is the series. So this is, if k is 1, 1 over 2 plus 2 over k is 2, 2 squared, 4 plus 1, 5. We don't always, sometimes, okay, I'm going to write them this time. If it's k equal to 3, I will have 3 squared plus 1, 10, right? Plus so on and so forth. So the general term here, it means we're adding terms that have this form. That's what I mean by general term. This is the type of terms I am adding. All right. Okay, now let's see the limit. The question is, when k goes to infinity of the ak. The limit, k over k squared plus 1. So let us compute this limit. Back to you. What do you think this limit is going to be? When k goes to infinity, what do you think this limit is going to be?
Zero.
0, because even you can look at it, when k goes to infinity, this is almost k, and this is almost k squared. So you'll have like 1 over k if you want. Or we can use, so this is going to go to infinity, and this will go to infinity. This is a scenario where dividing by k to the highest power, so we can divide by k squared, numerator and denominator. Okay, this is going to be equal to, this goes to 0, this goes to 1, is equal to 0. So the AK here, the terms, in other words, the terms, the individual terms, those are going to 0. Now, does this mean the series converge or diverge? Thus, the divergence test tells me what happened in the scenario.
No.
Exactly. When the terms become close to 0, here the divergence test is inconclusive. What do I mean inconclusive? Conclusive. Inconclusive means may converge or diverge. May converge or diverge. We don't know yet. Okay. So if the terms become close to 0, if the terms become small, at this stage, the divergence test is inconclusive. It means we actually don't know. The series may converge, the series may diverge. We have to learn a lot, and that's what we'll be doing this week to decide which way it goes. That's the situation. So if the terms don't become small, immediately diverge. If they become small, we have no idea. We have to learn a lot to be able to do that. And the reason, as I said several times, they don't become small, very small. They become small, but not too small. They still add up to something at the end. Okay, so now we're going to see the first test that will allow me to tell for some series if they converge or diverge when the term actually becomes small. So our first test today is what we're going to call the integral test. I will state it and give example. So the integral test. Integral. First, we're gonna work with a series with positive terms. So before I state the integral test, we're gonna say the following. A series is said to be with positive term if all the terms are positive. If all terms are positive. So sigma AK so that's the form. So the form is sigma AK where all the AKs are positive. That's what a series of positive terms mean. It means we're not allowing alternating positive, negative, positive, negative. So now the integral test. I'm gonna state it first. Tomorrow I'll prove it. Today I'll state it, give you an example. Tells me the following. Let sigma AK be a series with positive terms. With positive terms. Okay. And let f be a function. So we're going to introduce a function such that the following happen. So let us suppose, and I will explain clearly that AK is the value of a certain function at K. That assumed where f is a decreasing function. Okay. So suppose you have a sigma AK. And suppose that A of K, every term, is a function, f of K, where K is decreasing. Then, if the integral from 1 to infinity f of x dx converge, the integral converges, then the sum itself converges. And if the integral diverges, the sum will diverge. It means the integral and the sum behave similarly. Sorry. Sigma AK diverge. So the integral test compare the sum to an integral in an improper integral. That is, if the improper integral converge, the sum will converge. If the improper integral diverge, then the sum will diverge. So today I'm going to show you how this test works. Tomorrow I'll show you why the test works. I mean, why can we compare those two to each other? So I'm going to take the following example. So how to apply the integral test. So example number 1. Okay. Question is, use the integral test to decide if each of the following series converge or diverge. To decide if series converge or diverge. Means we're not going to find the values, but we're going to at least see if they converge or diverge. All right. Example number 1 is the following series. Sigma, let us say 1 over k, or 1 over k squared for now, k equal 1 to infinity. That's my series. So it's a 1 plus 1 over 2 squared plus 1 over 3 squared plus etc. etc. Okay, what does the integral test tell me? The integral test, so this is the ak first, is 1 over k squared. The integral test tells me, look at the function, take the function such that f of k is ak. So what is my function f? What they are talking about? So here it means let f of x be the function, f of x equal 1 over x squared. So that's the function that I'm gonna look at it. And here f of x equal 1 over x is x squared. If you plug in k for x, you get 1 over k squared. So we're gonna introduce a function whose values at k is ak. And the natural function is 1 over x squared. Now, when f is decreasing, the function f of x equal x squared, if we graph it, is decreasing. So f is decreasing. It's decreasing. Now, the integral test tells me that look at the improper integral from 1 to infinity of f of x. This one converge, your series will converge. That's really what it tells you. So now we're going to use the integral test. So we will look at the following integral. At the following improper integral. Integral from 1 to infinity of 1 over x squared dx. That's what it tells me. You look at this integral. If this one converges, your series will. Now let us remember the definition of this integral. That's an improper integral. The definition is the limit as t goes to infinity of the integral from 1 to t of 1 over x squared dx. Okay, so we have to look at this improper integral, which is equal to the limit as t goes to infinity of antiderivative of 1 over x squared. So this is, we rewrite it as x to the minus 2. That will have 1 over minus 2 plus 1, x to the minus 2 plus 1, evaluated between 1 and t. It means that's the limit as t goes to infinity of the following. Minus 2 plus 1 is minus 1, minus 1 over x between 1 and t. So it's going to be equal to the limit as t goes to infinity of the following. Minus 1 over t, minus minus, plus 1. So as t goes to infinity, this is equal to 1 over t goes to 0, because t blows up, this is equal to 1. It means that the improper integral 1 over x squared dx converges. The improper integral converges. So the integral test, will tell us that the series sigma 1 over k squared also converge. Okay, it doesn't tell me it converges to what. It does not tell me the value of the sum. It tells me that it converges. It means if we start adding those terms, we actually get close to a certain number. I mean, it will not keep blowing up. We get close to a certain number. Okay, and we try it tomorrow if you want. We can try to find what's the number they get close to. But the only thing I know that they will get close to a number, so I can start adding those numbers and find out what they will get close to. Okay, so that's how the integral test apply. So we introduce a function which is at k is 1 over k squared. It has to be decreasing for the theorem to work. And if the integral will converge, my series will converge. If my integral diverge, I could have almost immediately deduced that my series diverges. Right, so today I will stop at this point. So we studied the first test, divergence, tells me immediately if the terms blows up, don't go to zero, immediately diverge. But if the terms go to zero, I have no idea what happened to the series. Two things can occur. It can converge or diverge. And now what we're going to be doing is building tests to help me decide what will happen. So the first test we saw today is the integral test. And it's going to tell me that for some series, whether they converge or not. And tomorrow and the day after and after, we will see other tests to be able to decide what will happen for series. All right. Please, your homework is already on Pearson. Please do it. Don't be late behind in your homework. You will get lost before you know it. Okay.
I have a question.
Yeah. Class is dismissed. Anybody has a question can stay. Yes.
Two of them real quick.
No problem. Yeah.
So